Welcome to Algebra 1. My name is Dr. Monica Nigoy. I teach algebra along with other math courses to students and teachers of mathematics. I am also a math consultant in both mathematics and math education. Algebra 1 is an introductory course. Therefore, I will be introducing you to the concepts, skills, techniques, and methods of algebra. For most of you, this will be the beginning of your exploration or your journey into the new land of algebra. It's a new world because it has its own laws, its own definitions, its own objects, its own rules, its own language. And since I would like this not to be the end of your exploration, but only the beginning of a long one, I hope to interest you in the utility, the importance of algebra, excite you about the beauty of algebra, and stimulate you to solve some very interesting problems. My objective, on the whole, is that you will see the power, the beauty, and the fun of algebra. Now, if you go through these courses and you don't master everything you've seen here, or you can't do all the manipulative skills, that's okay. That's what Algebra 2 is all about. Algebra 2 follows Algebra 1, and there is where you refine the skills. You go a little deeper into the formulas. But in Algebra 1, what I'd hope that you would get out of this course is the general idea of the big picture, an understanding of the main concepts of algebra, and a competency, a basic competency to solve problems and equations. The last introductory remark I'd like to make is, and I'm sure you've heard this before, I've taught algebra to so many students and teachers who have many more students, and very often the reaction that students have is, why do I need to take this? Why do I need to take algebra? And after that question usually comes, when am I ever going to use this in my real world, in my life, in what I'm going to do out there when I leave school? Well, you will see that in this course, I've carefully selected activities, problems, methods, approaches, media, so that at the end of it all, you will realize that algebra is alive, is meaningful, is valuable, is relevant, and hopefully is fun and interesting, and I'll let you be the judge of those last two. Therefore, in the following, on the remaining part of this first lesson, I will be concentrating on two parts. The first, an overview of algebra as a subject, and the second, an overview of this course. Let's begin with algebra as a subject. What is the origin of the word algebra? Have you ever asked yourself that? You probably know that arithmetic has an origin. The word arithmos in Greek means number. So that makes sense that arithmetic came from the original Greek word for number. Algebra is different. It comes from the title of a very important book, and his name is Muhammad ibn Musa al-Khwarizmi. And that means Muhammad, son of Moses, the Khwarizmite, who wrote the book entitled Hisab Algebra wal Muqabala, with a more or less good pronunciation. And he wrote that in Baghdad around 825 AD. So we're talking about the 9th century. That book was then translated into Latin at the 12th century, and then it spread throughout Europe. In that title that you perhaps looked at and maybe jotted down, there are two verbs there, the al-jabr and the al-muqabala. I'd like to show you what they mean, and then I'll translate that title for you. Then you'll see where the word algebra comes from. Let's go to the graphic. Here is an equation. And while we're only in lesson 1 and we haven't solved equations yet, I'm sure you can follow me. This just means an equal sign, so the left quantity and the right quantity must always be the same. It's like a balance. Algebra means if I want to, for example, subtract 2x, the same quantity from both sides, we'll see later that we can do that when we're solving an equation as long as the quantity is the same on both sides. Well, what would I get? Assuming, of course, you've seen this, but I'm a little ahead of myself. When I subtract 2x from 3x, I think it makes sense that we get 1x. The y is left over. 2x minus 2x gives me 0, so that cancels. Y minus 6. Well, what I just did there, the fact that I subtracted 2x so that I could pass it in a sense to the other side where I get 3x minus 2x, which gives me the x, that's the meaning of algebra. Now, al-muqabala means if I have a same quantity on both sides, I can cancel it. I've got a y and a y. It's like taking the y off the balance. If I get rid of this y and I get rid of this y because they're the same terms, I get x equals -6. And I have solved the equation. Is about the science of solving equations, about the mechanics of how to pass terms on one side and how to cancel, all the things that we'll be doing throughout this course. It's not only about the methods of solving, but it goes through many, many, many equations and shows how to solve them. The title, through time, over the centuries, shrunk, got smaller and shorter, and just the word algebra remained, and that gave us algebra. So you know a little bit about the etymology of the word. What about the meaning of algebra? Well, you might have concluded from the title of what I called a very important book that it's about solving equations. And in a sense, that's true. There are really two phases in the history of algebra, and the first phase deals with elementary algebra. And even though there are only two, this first phase is a very long one. It starts way back at the beginning of recorded history in terms of mathematics. And that was the Egyptians, the ancient Egyptians. We have a document called the Rhind Papyrus. You might have heard about that. Lots and lots of equations, the beginning of algebra in the numerical sense. That was about 1700 BC, but perhaps it was thought up way before that, but we have no records. Then you go all the way to 1700 AD. So we're talking about over 3,000 years. That's the first period. And in that whole period, really, equations, the solutions of equations, linear equations, quadratic equations, cubic equations, all the equations we're going to talk about, and those you'll see in Algebra 2, are the essence, the focus of algebra. That is called elementary algebra, and it's the algebra that we see in textbooks in school mathematics. So it's basically what we're going to cover. We're doing elementary algebra. Some people call it the generalization of arithmetic. That's more or less true. It is that, but algebra is even more than that. And now the second phase, even though we're not going to do a lot of it, we're just going to touch on it in one chapter at the end of this course, on the matrix chapter, the one that deals with matrices. I believe it's chapter or lesson number 26, if I'm not mistaken. The second phase is a much more recent phase. It's only about a couple hundred years old, and it's called modern algebra. It's an abstract algebra where when you see X's and Y's and A's and B's, letters, they don't necessarily stand for numbers. They stand for points, vectors, matrices, things that are not a number like you and I are thinking of numbers right now. And in those algebras, algebras of vectors or algebras of matrices or algebras of quaternions, things happen differently. It's another land, it's another world. It has its own rules and its own languages. To give you an example, in matrix algebra, which you will see later on, A times B is not equal to B times A. Well, that's shocking, because when you think of numbers, 2 times 3 equals 3 times 2. That's commutative. We know that. So you see the rules are different. So abstract algebra, Modern algebra is what we sometimes see either in an advanced high school course or in college. Algebraic symbolism. That's also a very important question. If we follow the symbolism of how it developed, it's parallel to the development of its history, because as the symbolism became simpler and easy to use, algebra made great advances in its evolution. There are three phases in the symbolic development of algebra. One, the rhetorical phase, where the different civilizations used words from their own language to describe problems or solve equations. The second was the syncopated phase, where they began to use abbreviations of words, and I'll show you a few examples of that. And the third phase, the one we are presently in the 20th century, is the symbolic phase, where almost all words were dropped, and the Egyptians, the Babylonians, the ancient Greeks, for centuries just used the rhetorical phase. They were in the rhetorical phase, and they used words and words and words to write sentences. And when you think about an equation, when you say 3 times a number equals 5 times another number plus 7, we can write that in just a few symbols today. They'd have to write the whole thing out. There was no symbol for multiplication, for addition, for exponents, for fraction lines, for equal signs. Just begin to imagine writing algebra without the alphabet or the language of algebra, which we have today. It was cumbersome, it was tiring, it was tedious, and it was long. And very often, because of those obstacles, they couldn't progress into more advanced algebra. The syncopated phase began about the 3rd century, we believe, because we're not sure about the exact dates of Diophantus. But Diophantus is a Greek mathematician, and he wrote a very important book called Arithmetica, Arithmetic. And I'm going to give you 2 symbols that he used, which was a great advancement, great progress compared to the hundreds or even thousands of years before him. And in this next visual, you're going to see the 2 symbols he used. He used many others, but these are very interesting. One, he used for our present day x, which is the most common variable we see. He used the little letter you see there, which is an S, and that comes from the word arithmos, which is number in Greek, and he selected the last letter of the word. He could have selected the first, but he selected the last. So you see there, right there, he abbreviated the word and picked one letter. In the second line, you see our present day symbol for the subtraction sign, the operation called subtraction, and he used that shape that looks somewhat like an arrow but a little different, maybe like a little tent. That was the beginning of syncopation. Now that was in Europe, in Greece, but you have between about the 5th century, 3rd, 4th, 5th, until about the 12th or 13th century, Europe was slumbering in the Dark Ages, and we had the Arab and the Hindu mathematicians who were really carrying the load and making algebra progress. And some of the well-known names that you might encounter in the Arab Empire, I already mentioned Al-Khwarizmi. There's another one, Omar Khayyam. And in India, there was Brahmagupta and Bhaskara. Those are 4 well-known mathematicians throughout that period where Europe wasn't doing very much, and they pushed the syncopated phase further, introduced more symbols, more abbreviations. But what's really interesting for us here today is to know, when did algebra really begin to be written the way we write it today? Well, that occurred with the Renaissance mathematicians. And really, it started in the second half of the 16th century with mathematicians like Cardano from Italy, like Viette from France. I have a few examples of the notations that were developing end of the 16th century, beginning of the 17th century, and how they led all the way up to what we use today, which started at about 1700, late 1600s, 1700s. Let's go to our transparency that I've prepared for you and look at a few examples. Here we have the notation we would use today. 5x, I just picked 5 because I felt like it. I could have picked any number. 5x squared and 5x cubed. I'm sure you know how to read those. Well, here are some examples of the late 1500s. This one here dates to about the 1560s. This is a letter from the Greek alphabet, rho, which just means a thing, like a variable. This here is sort of like a square, because we often say square for that, and we'll see in this course why we call that x squared and why we call that x cubed. And this is just a little cube drawn out. Here's another invention. This is about the 1570s, a 5 with a 1 on top, a 2 on top, and a 3 on top. Here we have another notation where you just have a 1 circled, a 2 circled, and a 3 circled. Over here, this is about 1590, the French mathematician François Viette. 5n, n maybe for nombre, which is number or quantity, q for quadrus maybe, because that means square in Latin. X squared would be quadrus, or that's where the word quadratic comes from, and c from cubico, from cube. And here we have the notation that's now in the beginning 1600s, the early 1600s, 5a, 5aa, and 5aaa. Now you're saying, well, that's probably the same. Well, at that time it wasn't yet established that the letters at the end of the alphabet were going to be the variables, and the letters at the beginning of the alphabet were going to be the constants, the generalized constants. Here we have Descartes, René Descartes, 1637 actually, and he used 5x. Interesting, he put xx instead of x squared, but it soon became x squared, and then 5x cubed. That was, as I say, in 1637. In 1676, Newton used the same. So it would be correct to say that the present-day notation has been around for about 300 years. One final historical remark. The raw material of mathematics has always consisted of space and number for the longest time. Space gave geometry, number gave arithmetic. And what's important to realize is, although there's so much talk about algebra today, for the longest time, algebra was not born. There was geometry and arithmetic. So those two currents, the geometric current and the arithmetic current, gave birth to algebra. And when we look at the documents by the different civilizations, we see always that there's either an emphasis on the geometry or an emphasis on the numbers or the arithmetic. Now a little bit about the course. This course has followed the lead of the National Council of Teachers of Mathematics historical documents that were published at the end of the 80s, 89, and the early 90s. And they're called the standards. These are very important documents about the direction of mathematics as we approach the 21st century. It's also important to realize that they are endorsed by the leading mathematical associations of America. All of them, just about, the Mathematical Science Education Board, Mathematics Association of America, and so on. What do they say? They basically talk about some of the shifts that we should do in algebra to make algebra more important, more meaningful, more exciting for students. They say that certain topics should receive increased attention and other topics that need to receive increased attention are the use of real-world problems to motivate and apply theory, the use of computer utilities to develop conceptual understanding, and computer-based methods and graphing utilities for solving equations and inequalities. Those are 3 examples. Some topics that need to receive decreased attention are traditional word problems like coin problems, digit problems, age and work problems. The simplification of radical expressions, the use of factoring to solve equations and to simplify rational expressions, operations with rational. There are other such topics, but the major shifts in the new way of looking at algebra, I could summarize as 2. 1, the shift away from essentially being skill manipulation to a science of representation, representing situations numerically, symbolically, graphically, not just with equations, but in a lot of different ways. And the other shift is a shift away from presenting algebra as an isolated, dry, separate course that is disconnected from other areas of mathematics, science, and the world around us. So what is the reason for this change toward a new vision of seeing and interpreting and understanding algebra? One of the main reasons is the advent of new mathematical technologies like computers and calculators. They allow us to do so much more, and therefore the expectations are greater. So in our course, we will try to make algebra as alive as possible by studying many real-world situations. Almost always we'll start with the concrete. X and Y will have meaning to it. We will have graphing calculators so we can graph and look at pictures and look at numbers and look at graphs and connect the whole thing and make it make sense. So for us, algebra will be a means of representation, representing a whole lot of different problem situations. Now a little bit about the outline of the course in terms of the different sections. We first have 4 lessons, including this one, which introduce and lay certain ground rules for the ones to follow. Then we have 4 sections. We have the linear functions, quadratic functions, and then rational and exponential. And then we have 2 sections at the end on systems of equations and inequalities, and the last section with 2 lessons are giving you just a flavor of a whole new branch of mathematics that's very exciting right now, and that's fractals and chaos. It's just a touch of it, but to get you excited, hopefully. In each chapter, and in each section rather, we start with some explorations, so you get a feel, an intuitive feel of what's going on. Then we examine graphs, then we do some problem solving, then we do math modeling, you'll see what that is, and then we conclude on the properties. So after 7 lessons, you should get a good idea of what a linear function is and how to solve linear equations. The same thing for the other categories. Since there are only 30 lessons, and there are 30 minutes each, that's not a whole lot of time compared to how long an algebra course lasts in real school. So each lesson is really packed with information. If you feel that at the end of a 30-minute lecture you've not quite got it, well, there's 2 things you can do. You can rewind, but more importantly, there's a workbook that I've designed to go along with it. And what I do is I take the concepts further. I extend, I explore, I explain further, so that if you're not quite clear, you'll see that the problems are worked out for additional understanding, not just drill and practice, but a lot of thinking. History. I use history, as you saw in this lesson, every now and then, so that these mathematicians can come alive to you, to humanize the subject. They're not people who are gone and dead and forgotten about and boring. They had a life like you and I. So every now and then I like to talk a little bit about the civilizations or the people or the mathematicians to make it more alive, more human. I use a variety of media. That also is a way of maybe keeping you awake through this course that you might think, oh, I don't like algebra. You don't know that. Don't have any preconceived ideas. We use about 6 different media. 1, we have lecture, me talking, and I'll be talking much less than I'm doing right now. Then we'll have the whiteboard. We've already visited that. It's a modern blackboard. It's a whiteboard. It's on my table. And then we have the transparencies. You've seen a transparency also where I had all those powers of 5, 5x, 5x squared, and 5x cubed. And then we have base 10 blocks. We have some radioactive dice that I made. We have some triangles. We have some colored tiles, multi-link cubes, the Algebra Lab gear, some circles or discs that I've made, a measuring tape. And then in 3D we have multi-link cubes that are built to make bigger cubes, so color-coded, base 10 blocks, 1,000. Here we have the geoboard that we're going to visit. And then we have a whole lot of things that I'll be making. Here I made some polygons, and we'll make some cubes and other things out of paper. So this is not an elementary course. This is not a primary school course. This is algebra. But all of these help you visualize what's going on. And there are 2 more media. I told you there were 6. Calculator, the graphing calculator. We are going to integrate the use of the graphing calculator throughout the course. Lesson number 4 will give you an introduction, and then we'll work slowly in every single lesson. And finally, you have the computer graphics that you've already seen a couple come up. There's nice results that come up already printed by the computer. Every now and then they'll come up to either announce things coming or recap what we've said. In terms of the course still, a couple of more points. Integration. I like to teach algebra integrated. So it will be integrated following subject areas: geometry, calculus, statistics, discrete mathematics, number theory, and other areas. And yes, this is Algebra 1. Don't get scared away by those titles. You'll see how easy everything is, how natural, how logical, and how everything makes sense. One more point, action verbs. We are going to use action verbs throughout this course. Explore, investigate, experiment, discover, question, conjecture, analyze, review, present, solve, conclude, etc., etc. You are going to be in the driver's seat with me. I'm not just teaching to you. You're not just receiving. You are active. You are going to do what I'm doing at the same time. You are going to ask questions and you are going to answer them. Okay? That's the only way you can learn and understand what I'm going to teach you. And the last point I want to make about this course is, we said that time is precious. We only have 30 times 30 minutes. So I want to use every bit of that to teach you new and exciting things. So if ever you realize that you need a little review on some of the pre-algebra concepts that you've already learned, such as how to combine signed numbers, how to work with exponents, how to combine fractions with the different operations, just go back to your pre-algebra and review those concepts so that you're ready for algebra. Since we have just a few more minutes, and I said that problem solving and being active is the center focus of this whole course, I want to leave you with a problem. And here it is. Take a paper and pencil, or do this mentally, and follow with me. It's called, think of a number. Add 4 to that number. Then multiply that sum by 3. Then subtract 9. Then multiply by 2. Then divide by 6, and finally subtract the original number. Now if I've gone too fast, stop the tape, rewind, and do it again. And I bet you that no matter what number you picked, you found 1. Am I right? Let's use algebra for the first time, the language of algebra, and let's explain why no matter what number you picked, you would get 1. Think of a number. Well, x can be the generalized number, any number. We want to add 4. That's the first step. Once we've added 4, we want to multiply the whole thing by 3. Well, we will see that this is called the distributive law. That means 3 multiplies x, and 3 multiplies 4, because it multiplies both quantities inside. The next thing I said was subtract 9. Well, 9 is a constant, so I can take 9 away from 12, so I would get 3x plus 12 minus 9, I'm left with 3. After that, I said multiply by 2. Well, if I multiply by 2 this quantity, 3x plus 3, I get, again, the distributive law. 2 times 3x is 6x. 2 times 3 is 6. Then it says divide by 6. Well, if I divide both terms by 6, 6 over 6 is 1, 6 over 6 is 1, I'm left with 1x plus 1. The last thing I asked you to do was subtract the original number. Well, if I take away, subtract x, which was my original number, I'm left with 0 here, because x minus x is 0, and I'm left with a 1. We just used the language of algebra to go from the specific to the general, from the particular to the universal. No matter what starting value you had in mind, you would end up with 1. That's quite powerful. It's also fun. Try making up some of those problems. You'll find a few more in your workbook. I'd like to leave you with one more problem. It's fun also. Take a calendar. You might have one in your house. It can be any month of any year. Select a square, 3 by 3, meaning it contains 9 days. For example, here I have January of 1997, and I selected that red square of 9 days. Each day has a number. Add up those 9 numbers. Once you've computed the sum, divide by the central number. Can you predict what you will find? Well, you will find 9, no matter what square of numbers you began with. Try to prove that, just as we proved the previous problem. Perhaps you've begun to see that algebra is quite powerful. It's a problem-solving tool. It's many things. It's also a language. Algebraic notation is the language of mathematics, just as arithmetic notation is the language of numbers. The evolution of numbers